So it's a pleasure to be here. What I'd like to do is share with you a couple observations I have about what the challenges are of getting to Exascale. And actually the last talk was a great setup. I'm going to come back and talk a little bit about Legion and Singe and use those as examples when I get to the parallelism and programmability part of this talk. But I'll start with efficiency. Let me start out that I spent a lot of time in Washington trying to convince decision makers that they actually should spend money on this. And it's really for twofold reasons. One is that supercomputers have really become the instrument of choice for a lot of science. It's become the third tier of experiment and theory, and actually people do a lot of discovery with compute. If they have good models of things, they can discover things that weren't known previously. And the people with the best computers, it's like the people with the best telescopes or the best particle accelerators, are the ones who get the best discoveries. So if you don't invest in that, you're behind. But just as computers are an instrument for looking at nature and discovering things you didn't know before, they're also a great instrument for looking at your business and discovering things you didn't know before. And exactly the same facilities and exactly the same type of computers are behind what a lot of people are referring to as big data. It's data analytics, taking a large data set that you didn't collect from an accelerator or from a telescope, but rather you collected from point-of-sale terminals or monitoring traffic of some kind having to do with your business, and drawing information out of it that's actionable that you can use to make decisions to improve things. And it turns out it's exactly the same sort of things you need to make. Power-efficient processors, very low latency, high bandwidth communication, and good storage systems for both. You may provision them slightly differently, but it's the same components. This is an exciting time to be working in the field because things are changing. Changing very rapidly. Now, a lot of people are saying, oh, well, Moore's law is over. That's not the case. This is a chart that's due to a different Moore, the late Chuck Moore, who was CTO of AMD at the time. He did this chart. Moore's law is the top line here, the red dots with the line extrapolated through them. It's alive and well. We get more transistors every year. The problem is we're not able to get as much performance out of those transistors as we once did because constant field, what's called Denard scaling of how we build our circuits, has ended. And in fact, what you see here is starting in about 2000, 2005, all of the other curves here have kind of flattened out. And that's basically because we're able to make more transistors, we're not as able to turn them into performance. There's a great talk given by Bob Colwell, let me jump 2 slides ahead here and I'll come back, at the Design Automation Conference back in June, where basically what he says, Moore's law gave us more transistors, Denard scaling made them useful. We no longer have Denard scaling, that's the scaling we got of supply voltage as we change gate length to keep the field across the device constant. And as a result, we get all these transistors, we can't actually afford to power them all up at once. The bottom line is that it used to be when we got a new semiconductor technology, we got almost a factor of 3 in performance per watt out of it, 2.8 if you work all the numbers out. Now when we get a new semiconductor process, we get about 20%. And as a result of that, we're not able to use that process to get that historic rate of performance improvement, about 50% a year, that we got in the 80s and 90s. There was recently a National Academy study, I show the little booklet cover here, about scaling computer performance, game over or next level. And what it concludes is not only is it important to the computing industry that we solve this problem of continuing to scale computing performance, it's important to the whole economy. If you look at things like automobiles or aircraft, much of the value added today is being added by their information systems. The average car has over 50 processors in it doing various things. Many of them are our own Tegra processors, very, very popular with the auto manufacturers. And to continue to offer features, they need headroom. The performance of those processors has to scale. They're 100% busy with the features they have today. If we don't scale the performance of those processors, innovation in those fields will stagnate. With automobiles, it's not about the mechanical engineering, it's about the software engineering. So how do we get from there to here? Let's at least talk about the here part first. This is a machine that's number 2 on the top 500 list, but it uses a technology that has all 10 spots on the green 500 list. You can get a good position on the top 500 list by writing a big check or perhaps striking an amazing deal with the person selling the processors, but you can't cheat on the green 500 list. It's about how many teraflops of WinPack you get per watt. And the Kepler GPUs behind Titan individually are 7 gigaflops per watt. Unfortunately, we have to drag this very power inefficient CPU along with us on every node, which brings the average down to about 2 gigaflops per watt per node. The thing that I think it really sets Titan apart from some of the other machines on the top few, the top 500, is thanks largely to the people at Oak Ridge. There are lots of real science applications running on Titan today. and it's over 2 gigaflops per watt. The number one machine on the green 500 list, the Sabami machine at Tokyo Tech, is close to 4 gigaflops per watt, using exactly the same processors by just eliminating some of the waste in the balance of system, in particular in the CPU. So that's where we are today. This is our roadmap. You are here at 20 petaflops, 18,000 GPUs, 2 gigaflops per watt. Our goals, and to put a machine on the floor in 2022, which is the goal, we really need to have the components in 2020, are 50x in performance. I'm not too worried about that. What I am worried about is the 25x in performance per watt, and the fact that I'm going to need 10 billion threads working in parallel to fully use this machine. Let me talk about the efficiency one first. When I was on the faculty at MIT, I consulted for Digital Equipment Corporation, a once great computer company, and they had this rule that when you were presenting to anybody of rank of vice president or above, you weren't allowed to use a log scale on a plot because they wouldn't understand it. So I sort of always had the habit of going back to linear scales, just in case there's a vice president in the audience. But anyway, this is a plot of gigaflops per watt versus calendar year, and the green line shows what we need to achieve to reach exascale, and the blue line shows what we're going to get from process. Now I've determined that this efficiency gap winds up being 25x. The overall efficiency gap is 25x. We're going to get about a factor of 2 from process. So there's about a factor of 12 left. How are we going to get that? Well, it's going to have to be from architecture and circuits. That's what's left when you take the process away. And here's an example of what you can get from circuits. This is some work we did. It's actually a Stanford PhD thesis, a figure out of it here, on signaling. So it turns out that communication burns a lot of the power in modern processors and in modern GPUs. Moving bits around actually accounts for more power than doing arithmetic. And the way we move bits today is horribly inefficient. Everybody sort of learns in their introductory logic design class, which I actually used to teach here at Stanford, that you send a 1 by signaling at the power supply and a 0 by signaling at ground. And in fact, if you assign somebody to do it as inefficiently as possible, that's what they would come up with. It turns out it's a horrible waste of energy to signal that way. If you look at the essential energy you need to overcome the fundamental noise processes you're dealing with, it's far less. And so these curves actually show the performance energy trade-off of a number of different signaling systems. The black dots at the top are the conventional using the power supply to signal. It's slow and high power, which is the wrong direction. And this basically shows that that tends to be 200 femtojoules per bit millimeter, which is a figure of merit here. Previous work got down to the 20 to 30 femtojoules per bit millimeter, but very slow. Those are sort of the green, the red triangles there. And this thesis basically was able to kind of reproduce those energy levels, but at higher speeds. We have some stuff in the labs right now at Nvidia we're very excited about that's even lower energy and 20 gigabits per second. It's an order of magnitude off the scale in speed to the right and lower energy than anything on the scale. So what this shows is that circuit innovations can give you order of magnitude improvement in energy for very fundamental things like moving bits around, storing bits, reading bits from memory. There's huge opportunities for improvement there, and that's part of how we're going to close the gap to exascale. So I've determined there are no vice presidents in the audience. We've reverted to the log scale here. So 2.2x in process, 3x in circuits. There's still a gap there. How do we close that gap? Well, we do that through architecture. And one of the things I really like to drive home to people is what the trade-off is between single-thread performance and efficiency. This is another Stanford PhD thesis, figure out the Stanford PhD thesis, one of Mark Horowitz's students. And what he did is basically implemented a number of different types of processors and showed the trade-off between performance, this is single-thread performance in MIPS, against energy per instruction. And what you see is that the very complex machines like you would get with an Intel Haswell are off the chart up and to the right. But even at things that are sort of at the very high end, ARM cores, an A15 or so, or an A57, would be very much like the D4 point here, where you're spending enormous amounts of energy, order of 3x the energy of an efficient core, to go a little bit faster. And as you see by the slope there, as you want to go faster yet, the curve gets very steep, and you wind up spending enormous amounts of energy to make a single thread go faster. But if you have a lot of parallelism, that's a huge waste. You'd much rather be at one of these lower points And what you see is once you drop down from the sort of peak performance of about 1800 or 1900 MIPS, even to around 14 or 1500, you don't want to be an out-of-order core anymore. You're not, the black lines are not on the Pareto-optimal frontier. You want an in-order core, very simple, and you know, a 1 or 2 issue in-order core winds up being very energy efficient and still very high performance. Now there are a lot of simplifications there, but it sort of illustrates the point that if you look at roughly comparable technologies, this is the Intel 32 nanometer technology, which is roughly comparable to the TSMC 28 that our Kepler K20s and K40s are implemented in. We execute at 140 picojoules per flop. And I actually still think that that's scandalous, because more energy is going into things that aren't flops than are, and I would like to reverse that balance, and more of the energy is going into flops. But it looks really good compared to a CPU, which is more than an order of magnitude more expensive in picojoules per flop. And most of the flops in the number for the 1690 picojoule per flop are coming out of AVX. If you took the SIMD extension away, it would be far worse. The actual raw processor is extremely inefficient. So architecture, we plan to get at least a 4x improvement from. We've got a lot of different projects, you know, in the labs, and if even a few of them pan out, we'll cross this 4x gap and close that. So, so just to sort of sum up, closing that 25x efficiency gap is probably the thing that worries me the most about the Exascale goals. We're going to get 2x of it from process, 3x from circuits, things like more efficient signaling, SRAMs that are more efficient, you know, more clever ways of building arithmetic units. And then we're going to get 4x of it from architecture, largely by getting rid of overhead. If you think about it, doing a floating point operation takes about 20 picojoules. Even our very efficient GPUs are 140, which means it's sort of 7 to 1, you know, total energy to energy in arithmetic. I think that we can get to 2 to 1 by really just being very, very, you know, meticulous about looking at where the energy goes and driving waste out of the system. And if I had more than 20 minutes, I'd have a half a dozen examples I could give you of ways to do that. But let me go to the programming question. So it turns out that people always say, well, programming is going to be, you know, very, very hard, but it doesn't have to be. It's that way because we make it hard. And the previous speaker, you know, mentioned that, you know, they're going to have to recode all their applications for Exascale. I agree with that. I think it'll be a gradual thing. We need to run the existing applications, and over time they'll be recoded to really use the capabilities of the machine. But we don't want to recode them more than once. And the situation today is that people code machines, and they code them in very target-specific ways. Because to get performance out of the machine, they have to manually decide on how it's mapped, on how to, tasks are assigned to threads, how those threads are assigned to processors, how the individual leaf tasks are implemented to best exploit the characteristics of the underlying core, and how you stage data up and down the memory systems to exploit the memory hierarchy. And moving even to a new machine of the same class is a huge effort to recode to get the performance back. That often goes backwards when you get the new machine, even though it should have gone forward. That's because we're operating at far too low a level. So this is a cartoon of a simple molecular dynamics code, at least the part that computes the forces, not the part that pushes the molecules or rebuilds the neighbor lists. And this is what the code should look like, where it's simply iterating over sets. I simply say, for every molecule that I have, and that may be you know, 10 to the 8th, for every neighbor of that molecule, and depending on my radius, that may be, you know, 10 to the 3rd. For every force, maybe I'm doing electrostatic forces and Lennart-Jones and van der Waals. I'll basically you know, have a procedure I'll call, but then I'll basically say reduce sum over all those forces. And so I don't need to explicitly synchronize here. The synchronization is implicit in that reduction. I can't do the reduction until I've computed the forces. So I don't need to do barriers, I don't need to do locks, I don't need to manage any of that stuff. This is a simple program because it's machine independent. I'm not saying anything about what the target looks like here. You know, how many nodes, how much memory in each node, how many cache levels. All the parallelism is expressed. I could even inside these force calculations, if I wanted, break out the dependency graph of individual multiplies and adds and make each of those an independent task. I'm not in the code saying how I'm taking tasks, the fundamental atoms of work, and grouping them into threads. I'm leaving that for the programming system. And there's no explicit synchronization. All the synchronization is implicit in the semantics of the code. And so that makes it easy. Now I do have some friends that like to impress their colleagues with how smart they are. So they like to write the code in a way that makes it hard. because then they can show how clever they are. No mere mortals could write code like this, only super programmers. And so they fork threads and they acquire locks and manipulate structures and then unlock things. And they usually wind up unloosing a few rounds into their feet or more vital parts of their body, because it's very difficult to write code like this correctly. My colleague Jim Laris, who's now dean at EPFL, he was at Microsoft when he did this, wrote a tool that basically analyzed code for synchronization errors. And every piece of Microsoft code they ran it on, it found errors. I guess this shouldn't be a surprise. You know, even the code written by their best programmers, they would be, you know, acquiring a lock and then modifying a data structure, but it wasn't the right lock for that data structure. And then they would be, you know, releasing things in the wrong place before the mutations were done, with all sorts of subtle errors that you would run the code for hours before finding, and then it would blow up. So human beings were not meant to code this way. And it really is something that I learned when I was coaching youth soccer when my kids were smaller, that the biggest piece of advice I was always giving them is don't steal the ball from her, she's on your team. And that it was an issue of teamwork. People were not playing their positions. It was, you know, like all the kids, you know, in a little fur ball around where the ball is. And here the players are the programmers, the tools, and the architecture. And the problem is that the programmers are trying to play all the positions. And yeah, like most team efforts, building a team is a matter of establishing respect and trust between the team members. The reason why the programmers are doing this is that they do not respect or trust the tools, and in some sense, the tools give them good reasons for this. But it is possible to write good tools. And if you write good tools, these are the roles, these are the positions that these different players on the team should be playing. The programmer is supposed to write the algorithm and express all of the parallelism and the locality in an abstract way. And I think the Legion example that was in the previous talk is a great example of one way of doing this. The tools do combinatorial optimization to decide how to make mapping decisions, how to map atomic pieces of work into threads, how to map those threads onto processors, how to lay out data in memory, and how to stage data up and down storage hierarchies. And some of these tools run at compile time, some of these tools run at runtime, because very often you don't know things until you get to runtime. And then I almost hate to say this as an architect, but the job of the architecture is to get out of the way. There's sort of fundamental resources in the machine. There's arithmetic resources, there's storage resources, and you should be able to use the arithmetic at full capacity and to use the storage in the way that's most convenient for you and not be constrained by things. So the workflow that we envision for moving to Exascale, what will enable you to recode your huge million-line codes only once rather than for every new machine and for each different vendor that comes along, looks like this, where you have target-independent source code, much like that molecular dynamics code. You express all the parallelism, the abstract locality. You've got a set of mapping tools that make these decisions that are machine-specific, and they come up with a reasonably good executable. And then if you're not happy with that, you run some performance analysis and visualization tools, decide where you could do better, and write some mapping directives that give more insight to these tools, but you don't pollute your source code with machine-dependent information. That's a separate set of directives that basically targets it to a particular machine. So I've been given a yellow card, and before I get the red card here, let me tell you a little bit about our vision for Exascale. This is sort of our sketch of what an Exascale system will look like, with a processor chip that has both throughput optimized cores, think of those as the GPU cores, and latency optimized cores, think of those as the CPUs. Lots of memory that we can configure both as scratch pads and as caches depending on what the application wants, and a network. And recently we've been actually pushing a community effort with a bunch of both networking vendors, Juniper and Cisco, OEMs like IBM, Cray, and HP, and other processor vendors to open this ecosystem up, because there are some vendors that are trying to lock it all up. They want to integrate a NIC onto their chip, build their own fabric chips, and everything has to come from them. We would like you to be able to build machines with the best of breed accelerator, CPU, and networking fabric. And our goal is to have sub-microsecond latency, scalable bandwidth, support for small messages, 50% efficiency at 32 bytes, 20% for an 8-byte put, support for global address space, PGAS, collectives, and atomics, all the great things that people want. And basically what we're doing is we're coming up with a standard for the API, so you can build whatever NIC you want. All the software will be able to talk to it with one set of calls into that API. And the NIC router channel. So anybody can build their own NIC, anybody can build their own router as long as you support the protocol. So I think I'm about to get the card. So let me wrap up here. It's really kind of a fun time and a great thing to be working on. And it's not just for building a few exascale machines. It turns out this same problem of efficiency and programmability affects our entire product line, from supercomputers down to cell phones. And so whereas we used to get enormous gains, each of these jumps in the old days was a jump of 2.8x with each different process node. Now it's more like 20%. So even over this nearly decade-long period, we're only going to get 20%, or rather 2x out of process. We see the way through architecture and circuits to close this 25x performance gap. The other big challenge of exascales is how to take our codes and make them use 10 to the 10th threads in an environment that's heterogeneous and with deep storage hierarchies, and where a lot of the energy is involved in moving data up and down that storage hierarchy. So if you do it poorly, you're not going to get anywhere near your peak performance. And we see the way of doing that is to get programmers and tools and architectures to play their correct positions and to build programming systems that let you express the algorithm and all the parallelism of the abstract locality, and they make the difficult mapping decisions, because a programming system can try out literally hundreds of thousands, millions of ways of laying the data out and come up with far more clever solutions than human beings can. We should let the human beings do what they're good at and the tools do what they're good at. So with that, let me thank you for your time, and I'll take any questions if I have any time for that.